The wrench slipped from Lieutenant Masao Fujimoto's trembling fingers as he stared into the fuel tank cavity of the captured Boeing B-29 Superfortress. The mathematics were impossible. The tank capacity, the engine efficiency ratings, the aerodynamic profile, everything his team had measured over the past 72 hours, contradicted 3 years of Japanese intelligence assessments about American bomber capabilities. Around him, 8 of Japan's finest aviation engineers stood in stunned silence inside the cavernous hangar on Hokkaido's northern coast, where this massive aircraft had made an emergency landing after being damaged during a raid on Yawata steelworks. They had been told that American bombers were crude, hastily built machines that sacrificed quality for quantity. They had calculated that any aircraft capable of reaching Japan from distant Pacific bases would arrive with minimal bomb loads and insufficient fuel for return journeys. But the numbers emerging from their systematic examination told a completely different story. The B-29 sitting before them could fly farther, carry more, and operate at higher altitudes than anything in the Japanese arsenal, and it could do so while maintaining structural integrity that defied every engineering principle Japanese designers understood. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. The capture had occurred on November 29th, 1944. A damaged B-29 from the 73rd Bombardment Wing had limped away from its target in Kyushu, losing altitude and fuel after taking hits from Japanese fighters near Nagasaki. The pilot, facing the choice between ditching in the freezing waters of the Sea of Japan or attempting to reach Soviet territory, chose a third option, a wheels-up landing on a frozen lake in northern Hokkaido. The aircraft had skidded across, the ice coming to rest with its fuselage intact and most systems remarkably undamaged. Japanese forces reached the site within hours, capturing the 11-man crew and immediately recognizing the intelligence value of an almost intact B-29. This was the first Superfortress to fall into Japanese hands in conditions sufficient for detailed technical analysis. The aircraft was carefully transported to a heavily guarded facility near Sapporo, where the Imperial Japanese Army Air Service had established its primary technical intelligence unit. Lieutenant Fujimoto, a graduate of Tokyo Imperial University with advanced degrees in aeronautical engineering, had been assigned to lead the examination team. With him were specialists in engines, structures, armaments, avionics, and manufacturing processes, the best technical minds Japan could assemble. They understood that this examination represented perhaps their last opportunity to understand how America had achieved such devastating bombing capability. Their orders from Tokyo were explicit. Determine how the B-29 achieves its range, assess whether Japanese industry can replicate its capabilities, and identify any weaknesses that might be exploited in combat. The team began their work on December 1st, 1944, knowing that every day brought more B-29 seconds over Japanese cities. The external examination alone revealed disturbing realities. The B-29 was enormous, 99 feet long with a wingspan of 141 feet. It weighed 60,000 pounds empty and could carry loads exceeding 120,000 pounds at takeoff. Japanese intelligence had estimated the aircraft's size reasonably accurately from reconnaissance photographs, but seeing it in person drove home the scale of American industrial ambition. This was not an aircraft designed for short-range tactical missions. Every aspect of its configuration screamed strategic bombing, the ability to strike targets thousands of miles from base and return safely. The pressurized fuselage, uncommon in any military aircraft of the era, allowed the crew to operate at altitudes where Japanese fighters struggled to reach. The defensive armament consisted of 12 50-caliber machine guns in remote-controlled turrets, eliminating the need for exposed gunner positions that created drag and structural weaknesses. Fujimoto's team carefully documented every external feature before beginning the internal examination. The skin panels were flush riveted, a technique that reduced drag but required precision manufacturing that Japanese factories had largely abandoned due to material shortages and time pressures. The Americans had not compromised. Every rivet sat perfectly flush, every panel aligned with tolerances measured in hundredths of an inch. The landing gear was robust beyond anything Japanese engineers considered necessary, clearly designed to handle repeated takeoffs and landings at maximum weight. Japanese bombers, built as light as possible to maximize range, often suffered landing gear failures under combat loads. The B-29's gear looked like it could handle twice the aircraft's rated weight without complaint. The engine examination began on December 3rd. The B-29 was powered by four Wright R3350 duplex Cyclone engines, each producing 2,200 horsepower. These were the most powerful aircraft engines in operational service anywhere in the world. Commander Takeshi Nakamura, Japan's leading expert on radial engine design, supervised the engine team's work. They began by removing the cowling from the No. 3 engine, the most accessible and least damaged. What they found inside challenged every assumption about practical limits of reciprocating engine design. The R3350 displaced 3,350 cubic inches, far larger than any Japanese aircraft engine. It achieved its enormous power through 18 cylinders arranged in 2 rows, advanced supercharging, and metallurgy that Japanese industry could not replicate. Nakamura carefully measured the cylinder bore and stroke, examined the connecting rods and crankshaft, and studied the supercharger installation. Each component represented manufacturing capability that Japan had never possessed. The cylinders were forged from steel alloys that maintained strength at temperatures exceeding 400 degrees Celsius. Japanese engines used inferior materials that limited operating temperatures and power output. The crankshaft was a single forged piece, machined to tolerances that required precision equipment Japan's bombed factories no longer housed. The supercharger installation used advanced ducting and intercoolers that increased power output while managing heat that would destroy lesser engines. Nakamura spent an entire day examining just the supercharger system, marveling at engineering that solved problems Japanese designers had barely begun to address. His preliminary report noted that the R3350 represented at least a decade of development advantage over Japan's best engines. Even if Japanese factories had intact production facilities and unlimited materials, they lacked the metallurgical knowledge, precision manufacturing capability, and testing infrastructure needed to replicate this engine's performance. The fuel system examination revealed the source of Fujimoto's initial shock. The B-29 carried fuel in multiple tanks distributed throughout the wings and fuselage, a total capacity of 9,188 gallons. Japanese intelligence had estimated perhaps 6,000 gallons based on observed mission profiles. They had been off by more than 50%. 9,000 gallons of aviation gasoline weighed approximately 33,000 pounds, more than half the aircraft's empty weight. Carrying this fuel load required structural strength that defied Japanese understanding of practical aircraft design limits. Chief Structural Engineer Hiroshi Yamamoto led the team examining the B-29's airframe. They used ultrasonic testing equipment, carefully borrowed from damaged American bombers shot down over previous months, to measure wing spar dimensions without destructive disassembly. The main wing spars were machined from aluminum alloy extrusions of incredible size and complexity. Each spar was a single piece, running from the fuselage to nearly the wingtip, over 60 feet long without joints or splices. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. Yamamoto calculated the load-bearing capacity of these spars and arrived at numbers that seemed impossible. The wing structure could support loads exceeding 15 Gs, far beyond any combat maneuver or atmospheric turbulence the aircraft would encounter. This over-engineering was not wasteful American excess. It was deliberate design for reliability and longevity. The Americans expected their B-29 seconds to fly hundreds of missions over thousands of hours. Japanese bombers were designed for perhaps 50 missions before structural fatigue made them unreliable. The difference in design philosophy reflected different industrial capabilities and strategic thinking. Japan built aircraft to survive long enough to damage the enemy. America built aircraft to win a long war through sustained operations. The manufacturing quality visible in every structural component told its own story about American industrial capacity. The aluminum alloys used throughout the aircraft were uniform in composition and heat treatment. Japanese metallurgists had struggled for years with inconsistent aluminum quality as raw material supplies degraded and experienced workers were drafted into combat units. The Americans seemed to have unlimited access to high-quality materials and the industrial infrastructure to process them consistently. Rivet holes were drilled with precision that indicated automated machinery and statistical quality control. In Japanese factories, workers drilled rivet holes by hand, leading to variations that weakened structures and increased assembly time. The Americans had industrialized every aspect of aircraft production, applying mass manufacturing techniques that Japanese industry, organized around skilled craftsmen and small workshops, could not match. The pressurization system fascinated the technical team. Maintaining cabin pressure at 25,000 feet required sealing the fuselage to prevent air leakage while managing the structural stresses created by pressure differentials. The B-29's fuselage was divided into 3 pressurized compartments connected by a crawl tunnel that also held the bomb bay. The pressure vessel design used formed aluminum sheets riveted to heavy internal frames, with every seam sealed using rubber gaskets and special compounds. Japanese engineers had experimented with pressurized aircraft designs but abandoned them as too complex for wartime production. The Americans had made pressurization standard equipment on a production bomber, solving countless technical challenges and manufacturing complications that Japanese designers considered insurmountable. Lieutenant Kenji Saito, specialist in avionics and fire control systems, examined the B-29's remote gun turret system with particular interest. The Superfortress mounted 4 gun turrets, 1 in the nose, 2 on top of the fuselage, and 1 in the tail, each housing paired .50 caliber machine guns. The turrets were controlled remotely by gunners sitting at fire control stations inside the pressurized compartments. This system eliminated the need for gunners to sit in exposed turret positions, reduced drag, and allowed more sophisticated fire control through centralized computing systems. Saito had read intelligence reports describing the remote turret concept, but assumed they exaggerated American technical capabilities. Now, examining the actual hardware, he realized the reports had understated the sophistication of the system. Each gunner station included an optical sight connected through analog computers to the turret servos. The gunner simply tracked the target in his sight, and the computer calculated the required lead angles, adjusted for aircraft speed, target movement, and ballistic drop, then positioned the guns accordingly. The system allowed relatively inexperienced gunners to achieve hit probabilities that would require years of training with manual gun mounts. The analog computers that performed these calculations were marvels of mechanical engineering assemblies of gears, cams, and differentials that solved complex ballistic equations in real time. Japanese fire control systems relied on skilled gunners, making intuitive adjustments based on experience. The Americans had mechanized expertise, building knowledge into the equipment itself. The bomb bay examination revealed additional insights into American strategic thinking. The B-29 could carry up to 20,000 pounds of bombs, but the bay was designed for flexibility. Racks could be reconfigured to carry various combinations of large and small ordnance. Specialized equipment allowed for incendiary bombs, conventional high explosives, or even atomic weapons, though the Japanese examiners in 1944 had no knowledge of ongoing atomic bomb development. The bomb release mechanisms were electrically operated with redundant systems and manual backup. Japanese bombers used simpler mechanical release systems that sometimes failed under combat stress. The Americans had engineered reliability into every system, accepting additional complexity and weight to ensure consistent performance. By the end of the first week of examination, Fujimoto's team had documented enough technical details to fill several hundred pages of reports. But the true scope of American industrial superiority emerged not from individual systems, but from the integration of everything into a coherent whole. The B-29 was not a collection of impressive components. It was a complete weapons system designed for sustained strategic bombing across vast Pacific distances. Every design choice reflected an industrial base capable of supporting complex, expensive aircraft in large numbers. The precision manufacturing visible in every component required factories with advanced machine tools. The advanced materials demanded sophisticated metallurgy and chemical processing. The sophisticated systems needed designers with deep theoretical knowledge and practical experience. America possessed all of these advantages. Japan possessed none of them. The range calculations that had initially shocked Fujimoto became even more disturbing as the team analyzed flight performance data. With full fuel tanks and a typical 10,000-pound bomb load, the B-29 could fly approximately 3,300 miles, enough to reach Japan, from bases in the Mariana Islands, drop bombs on targets, and return safely. Japanese intelligence had estimated combat radius of perhaps 2,000 miles, assuming American bombers would follow Japanese design philosophy of minimal fuel reserves and single mission planning. The Americans designed for safety margins. They wanted their crews to return alive, their aircraft to fly again. This required extra fuel capacity, robust systems, and conservative operating procedures. Japanese doctrine accepted high attrition rates as inevitable. American doctrine sought to minimize losses through superior equipment and planning. The Wright R-3350 engines, examined in detail over multiple days, revealed additional layers of American engineering sophistication. The engine oil system used pressure regulators and flow controls that maintained proper lubrication under all operating conditions. Japanese engines required pilots to manually adjust oil flow based on temperature and power settings. A workload that contributed to pilot fatigue and engine failures. The ignition system used dual magnetos with separate spark plug sets, ensuring the engine continued running even if one complete ignition system failed. Japanese engines typically used single ignition systems that left no margin for component failures. The carburetor installation included automatic mixture control that adjusted fuel flow for altitude and temperature changes. Japanese pilots manually adjusted mixture, one more task in already overwhelming workload. Every system on the B-29 reflected the same design philosophy: automate what can be automated, provide redundancy for critical functions, and design for operation by trained but not superhuman crews. Japanese aircraft design assumed exceptional pilot skill and accepted that lesser pilots would fail. American design sought to make average pilots successful through superior equipment. One approach produced a few elite units capable of extraordinary performance. The other produced an entire air force of competent, reliable squadrons that could sustain operations indefinitely. In industrial warfare, the latter approach was proving decisive. Japan's elite pilots were dying faster than training could replace them. America's average pilots flew better aircraft and survived to gain experience that made them increasingly effective. The structural analysis team spent the second week of December conducting detailed measurements that would reveal the full extent of American manufacturing capabilities. Engineer Yamamoto had initially focused on the wing spars, but as his team expanded their examination to include fuselage frames, skin panels, and control surfaces, a disturbing pattern emerged. Every structural component showed evidence of precision manufacturing at a scale Japanese industry had never achieved. The fuselage frames were not hand-formed pieces, laboriously shaped by skilled metalworkers. They were stamped extrusions, produced by massive, hydraulic presses that could form complex shapes in seconds. Each frame was identical to every other frame of the same type, suggesting production tooling capable of producing thousands of components with perfect repeatability. Yamamoto requested permission to carefully remove one fuselage frame section for destructive testing. His superiors, understanding the intelligence value, approved the request despite the damage it would cause to the otherwise intact aircraft. The frame section, once removed, revealed manufacturing secrets that Japanese metallurgists had been seeking for years. The aluminum alloy was not a simple mixture of metals. Spectrographic analysis showed precise control of alloying elements copper, magnesium, manganese, and silicon in ratios that produced optimal strength to weight characteristics. More significantly, the heat treatment was perfectly uniform throughout the entire component. Japanese aluminum production suffered from inconsistent heat treatment that left some areas properly hardened while others remained soft and weak. The Americans had solved this problem through industrial processes that Japanese factories, even before the bombing campaigns, had never possessed. The metallurgical examination expanded to include samples from various parts of the aircraft. Skin panels, engine components, landing gear structures, and internal fittings were all subjected to detailed analysis. The results painted a comprehensive picture of American materials science advantages. Steel components used alloys that maintained strength at high temperatures while resisting corrosion and fatigue. Aluminum alloys were optimized for specific applications, some for strength, others for formability, still others for corrosion resistance in specific environments. Magnesium alloys, rarely used in Japanese aircraft due to material scarcity, appeared throughout the B-29 applications where weight savings justified the expense. The Americans had access to the entire periodic table and the industrial infrastructure to process exotic materials into useful components. Commander Nakamura completed his detailed analysis of the Wright R-3350 engines by mid-December. His report to Tokyo was titled Assessment of American Aircraft Engine Technology and Implications for Japanese Aviation Industry. The document ran to 87 pages of technical analysis, but the conclusion could be summarized in a single devastating sentence. Japan could not build engines comparable to the R-3350 with existing industrial capacity, available materials, or current technical knowledge. Even if American engineers provided complete blueprints and manufacturing specifications, Japanese factories lacked the machine tools, metallurgical expertise, and quality control systems needed to produce these engines in quantity. Nakamura estimated that establishing production capability would require 5 to 7 years of intensive industrial development, thousands of trained workers, and access to raw materials that Japan no longer possessed. The engine examination revealed specific technical barriers that seemed insurmountable. The cylinder barrels were forged from steel containing nickel and chromium in precise ratios that gave the material exceptional strength at high temperatures. Japan's nickel supplies, always limited, had been largely exhausted. The few remaining sources were allocated to naval construction and could not be diverted to aircraft engine production. The crankshaft forging required hydraulic presses capable of exerting thousands of tons of pressure, equipment that existed in only 2 Japanese facilities, both damaged by American bombing. The precision machining of the crankshaft demanded machine tools with accuracy measured in 10,000ths of an inch, machines that Japanese factories had never possessed in sufficient numbers. The supercharger impellers were cast using investment casting processes that Japanese foundries had experimented with but never mastered for production use. Beyond the immediate technical barriers, Nakamura identified a more fundamental problem. The R-3350 represented the culmination of 20 years of continuous development by Wright Aeronautical Corporation and its predecessor companies. It incorporated lessons learned from thousands of earlier engines, millions of test hours, and continuous refinement of manufacturing processes. Japanese engine development had proceeded in fits and starts, with frequent changes in direction driven by shifting military requirements and limited research funding. While American companies had been steadily improving radial engine technology throughout the 1930s, Japanese manufacturers had been trying to master liquid-cooled inline engines, air-cooled radials, and even diesel engines simultaneously. The dispersed effort meant that Japan had modest capabilities in multiple engine types, but excellence in none. The avionics examination team, led by Lieutenant Saito, made discoveries that were equally troubling. The B-29's electrical system operated at 28 volts direct current, similar to Japanese aircraft, but the similarities ended there. The American electrical system included multiple redundant power sources, 4 engine-driven generators, plus auxiliary power units that could provide electricity even with all engines shut down. Circuit protection was provided by automatic circuit breakers rather than the fuses used in Japanese aircraft. Every critical system had backup power supplies and alternate routing that kept equipment functional, even if primary systems failed. The electrical wiring itself was superior in every measurable way. American wire used copper of higher purity and conductivity than Japanese wire. The insulation was synthetic rubber that remained flexible at extreme temperatures and resisted deterioration from oil, fuel, and hydraulic fluid exposure. Japanese wire insulation, increasingly made from substitute materials as rubber supplies disappeared, became brittle in cold weather and degraded rapidly in contact with aircraft fluids. The radio equipment installed in the B-29 stunned Saito's team. They found multiple radio sets covering different frequency ranges and serving different purposes. A command radio for long-range communication with base, liaison radios for communication between aircraft in formation, navigation radios for receiving directional signals from ground stations, an identification transponder that automatically responded to friendly radar interrogation. The profusion of radio equipment suggested that American forces assumed constant communication would be maintained under all conditions. Japanese aircraft typically carried 1 or 2 radios, and commanders accepted that communication would frequently be lost due to equipment failures, atmospheric conditions, or battle damage. The Americans had engineered redundancy into their communications, ensuring that some radio system would remain functional regardless of circumstances. Each American radio used crystal-controlled frequency stability, the same technology that had shocked German engineers examining captured equipment in North Africa. Saito had read translated German technical intelligence reports describing American radio crystal manufacturing capabilities. Now, examining actual equipment, he confirmed that the Germans had not exaggerated. The B-29 contained over 30 precision quartz crystals distributed among its various radio sets. Each crystal was hermetically sealed, precisely ground, and marked with exact frequency specifications. Japanese crystal production, concentrated in small laboratories using hand-polishing techniques, produced perhaps 10,000 crystals annually for all military services. The Americans had installed 30 crystals in a single bomber and were producing hundreds of B-29 seconds monthly. The mathematics were impossible to ignore. The optical equipment examination revealed yet another dimension of American technical superiority. The B-29's bomb sight was a classified Norden device, one of America's most closely guarded military secrets. Japanese intelligence had sought information about the Norden site for years, knowing only that it provided extraordinary bombing accuracy. Now, with an actual site available for examination, optical specialists carefully disassembled the complex mechanism. What they discovered was an analog computer of stunning sophistication. The Norden site accepted inputs for altitude, airspeed, wind velocity, bomb ballistics, and target motion, then computed the precise release point for accurate bombing. The calculations were performed mechanically, using a system of gyroscopes, gears, and linkages that represented decades of development by American engineers and mathematicians. The site's optical system used lenses ground to tolerances that Japanese optical manufacturers associated only with laboratory instruments and the finest civilian cameras. The anti-reflective coatings on the lenses employed chemical processes that Japanese glassmakers had never mastered. The mechanical components moved in jeweled bearings that eliminated friction and wear, ensuring the computer's calculations remained accurate after hundreds of hours of operation. Japanese bomb sights, by comparison, were relatively simple devices that required highly trained bombardiers to mentally perform calculations the Norden site automated. One approach required years of training and exceptional mathematical ability. The other approach mechanized expertise, allowing adequately trained bombardiers to achieve results that Japanese could only approximate with their best specialists. By late December 1944, the examination team had generated over 1,500 pages of technical reports, drawings, photographs, and analysis. The documentation covered every system, component, and manufacturing detail they could observe without completely destroying the aircraft. Fujimoto compiled the findings into a summary report for transmission to Tokyo. The summary was necessarily selective, highlighting the most critical discoveries and their strategic implications. He organized the report around three major findings that emerged from the detailed technical analysis. First, American industrial capacity for precision manufacturing exceeded Japanese capabilities by orders of magnitude. The B-29 contained thousands of components that Japanese factories could not produce in required quantities with acceptable quality. Precision bearings, electrical components, hydraulic seals, optical elements, and structural parts all demanded manufacturing capabilities that Japan had never developed. Even relatively simple items like electrical switches and control cables showed manufacturing sophistication that reflected industrial infrastructure Japan did not possess. The gap was not merely technical, it was industrial, organizational, and systematic. Second, American design philosophy prioritized operational reliability and crew survival over traditional measures of efficiency. The B-29 was deliberately overbuilt in ways that Japanese engineers considered wasteful. Structural components had safety margins that seemed excessive. Systems had redundancy that added weight and complexity. Equipment was designed for maintenance by relatively unskilled technicians rather than specialists. These design choices only made sense in the context of sustained operations over months and years. The Americans were building an air force that could maintain operational tempo indefinitely. Japanese aircraft design focused on maximum performance for minimum weight, accepting high maintenance requirements and significant attrition rates. One philosophy assumed industrial capacity to replace losses and support complex logistics. The other philosophy assumed scarcity and improvisation. Third, the integration of advanced technology throughout the B-29 revealed systematic investment in research and development that Japan could not match. The aircraft incorporated recent innovations in aerodynamics, propulsion, structures, and avionics that represented cutting-edge technology in 1944. These innovations had not appeared spontaneously. They resulted from decades of research at universities, government laboratories, and private companies. The Americans had created an innovation infrastructure that continuously generated new technologies and rapidly incorporated them into production equipment. Japanese research and development efforts, always limited by funding constraints, had been further degraded by the war. Universities had lost faculty to military service. Industrial research laboratories had been converted to production facilities. Government research establishments focused on immediate tactical problems rather than fundamental advances. Fujimoto's summary report included recommendations that he knew would be difficult for Tokyo to accept. He recommended against attempting to replicate B-29 capabilities with Japanese resources. The industrial investment required was simply too large and would take too long to show results. Instead, he suggested focusing defensive efforts on the B-29's few weaknesses. The engines, while powerful and sophisticated, were complex and occasionally unreliable. They required careful operation and regular maintenance that might be difficult to provide under combat conditions. The pressurization system, while effective, could be compromised by battle damage that created leaks. The remote gun turrets, though advanced, had blind spots that aggressive fighter pilots might exploit. These weaknesses offered tactical opportunities but did not change the strategic reality that the B-29 represented an aircraft that Japan could not counter with existing resources. The report was transmitted to Tokyo in early January 1945. It arrived during a period of increasing desperation as American bombing campaigns intensified. B-29 seconds were now striking Japanese cities regularly, and Japanese defenses were proving inadequate. Fighter interceptions achieved some success but at unsustainable loss rates. Anti-aircraft artillery rarely reached the altitudes where B-29 seconds operated. The few B-29 seconds shot down were replaced within days by aircraft arriving from American production lines. Japanese losses, pilots, aircraft, ammunition, and fuel could not be replaced at all. The technical intelligence report on the captured B-29 confirmed what Japanese military leaders increasingly suspected. The war was already lost. American industrial superiority was absolute and growing. Every month brought more B-29 seconds, flying from more bases, striking more targets with increasing accuracy. The examination team received orders in mid-January to prepare the captured B-29 for flight testing. Tokyo wanted to understand not just the aircraft's technical characteristics, but its operational performance under actual flight conditions. This presented enormous challenges. The aircraft had sustained damage during its forced landing that required repairs. Japanese technicians had to fabricate replacement parts without access to American manufacturing specifications or materials. The engines needed servicing with lubricants and fluids that differed from Japanese standards. Most critically, finding pilots qualified to fly an aircraft of the B-29's size and complexity proved nearly impossible. Japanese pilots, trained in much smaller aircraft, lacked experience with four-engine bombers. The few transport pilots with multi-engine experience had never flown anything approaching the B-29's performance envelope. A test pilot was eventually selected from the small pool of Japanese officers with extensive multi-engine experience. Captain Hideaki Matsumoto had flown German-built Focke-Wulf Condor patrol bombers and understood the challenges of operating large, complex aircraft. He studied the captured B-29's flight manual, translated hurriedly by Japanese-American linguists who were themselves learning aviation terminology. The manual described flight characteristics, procedures, and limitations in exhaustive detail. American technical writing assumed pilots would follow documented procedures rather than relying on experience and intuition. Japanese flight manuals, typically brief documents covering basic procedures, expected pilots to develop expertise through training and practice. The cultural differences reflected in technical documentation paralleled the differences visible in the aircraft themselves. The flight test program began in early February 1945. Initial engine runs revealed immediate problems. The Wright R-3350 engines required starting procedures different from Japanese radial engines. They needed careful priming, specific throttle positions during start, and close monitoring of temperatures and pressures. Captain Matsumoto and his engineer carefully followed the American manual's instructions, discovering that the procedures worked exactly as documented when followed precisely. This contrasted sharply with Japanese aircraft, where starting procedures varied with temperature, humidity, and individual aircraft quirks that pilots learned through experience. The American engines were designed to operate consistently when procedures were followed correctly. Taxi tests revealed the B-29's size and weight. The aircraft required significant power to move, and its wide landing gear track made ground handling different from Japanese bombers. The brakes, hydraulically operated and powerful, required careful modulation to avoid nosing over. American pilots trained extensively in these aircraft before flying combat missions. Captain Matsumoto was attempting to master the B-29 with minimal preparation and no instructor. The first flight, scheduled for February 15, 1945, was postponed twice due to mechanical issues and weather. When conditions finally aligned, Matsumoto taxied the massive bomber to the runway's end, advanced the throttles, and experienced acceleration that surprised him despite his preparation. The B-29, even without full fuel or bomb load, weighed far more than any aircraft he had previously flown. Yet, the four Wright engines pulled the bomber down the runway with authority, and the aircraft lifted smoothly at the documented rotation speed. The flight lasted 47 minutes and covered basic handling characteristics. Matsumoto found the B-29 stable and responsive despite its size. The controls were heavy but well balanced. The aircraft flew with a solidity that Japanese bombers, built as light as possible, could not match. Engine instruments remained within normal ranges throughout the flight. The pressurization system maintained cabin pressure, though at reduced levels due to seal degradation from months of company's inactivity. Landing proved challenging due to the aircraft's momentum and unfamiliar sight picture, but Matsumoto managed a creditable touchdown with only minor bouncing. His post-flight report noted that the B-29, while demanding in terms of pilot workload and systems management, was fundamentally a well-designed aircraft that rewarded proper technique with predictable performance. Subsequent flights explored performance at various weights and altitudes. The examination team carefully measured fuel consumption, climb rates, and cruise performance. The data confirmed theoretical calculations derived from earlier ground examination. With full fuel and typical bomb load, the B-29 could indeed fly over 3,000 miles, while maintaining altitudes that placed it beyond the effective reach of most Japanese defenses. The aircraft's service ceiling exceeded 30,000 feet, and it could cruise at that altitude for hours while consuming fuel at rates that still left adequate reserves. For return to base, Japanese interceptor fighters could reach these altitudes only through extreme effort, arriving with limited fuel and reduced maneuverability that made them vulnerable to the B-29's defensive armament. The flight test program continued through February and into early March of 1945, but the value of additional testing diminished as American bombing intensified and Japanese resources dwindled. The captured B-29 had revealed everything Japanese engineers needed to know about American technical capabilities. Further testing would not change the fundamental reality that Japan lacked the industrial capacity to counter this aircraft effectively. The examination team shifted focus from understanding the B-29 itself to analyzing broader implications for Japanese aviation strategy and industrial planning. Lieutenant Fujimoto was tasked with preparing a comprehensive assessment that would synthesize technical findings with strategic recommendations. This report, completed in mid-March, represented the culmination of 4 months of intensive examination and analysis. Fujimoto's strategic assessment began with industrial capacity analysis. He documented that Boeing's Seattle and Wichita plants, along with facilities operated by Bell in Georgia and Martin in Nebraska, were producing approximately 100 B-29 seconds monthly by late 1944. This production rate was accelerating as manufacturing processes improved and supply chains stabilized. By war's end, Fujimoto estimated American industry would deliver over 3,000 B-29 seconds, creating a strategic bombing force of unprecedented size and capability. Japanese aircraft production, by comparison, had peaked at approximately 1,500 military aircraft monthly in early 1944 and was declining rapidly as bombing destroyed factories, raw material shortages intensified, and skilled workers became increasingly scarce. The quantitative disparity was staggering, but more significant was the qualitative gap. Japanese production consisted primarily of fighters and light bombers designed for tactical operations. American production included heavy bombers designed for strategic campaigns that could be sustained indefinitely. The assessment examined American logistics infrastructure supporting B-29 operations. Intelligence reports documented massive base construction projects in the Mariana Islands, where runways, hardstands, maintenance facilities, fuel storage, and ammunition depots were being built to support hundreds of bombers. Supply ships arrived continuously, carrying spare parts, engines, propellers, tires, and the countless components needed to maintain a strategic bombing force. Fuel tankers delivered aviation gasoline in quantities that exceeded Japan's total monthly production. The logistical effort supporting B-29 operations represented industrial mobilization on a scale that Japan had never attempted and could not replicate. American forces operated with abundance while Japanese forces improvised with scarcity. Fujimoto analyzed the crew training infrastructure that produced B-29 pilots, navigators, bombardiers, and gunners. American training programs used dedicated training aircraft, standardized curricula, and months of instruction that produced competent crews capable of operating complex equipment under combat conditions. Training facilities in the continental United States were safe from enemy attack, allowing continuous operation and refinement of techniques. Japanese training programs, increasingly disrupted by fuel shortages, attacks on training bases, and desperate need for replacement pilots at the front, had deteriorated to minimal proficiency instruction. Japanese pilots reached operational units with basic flying skills but little preparation for combat conditions. American crews arrived in the Pacific Theater after hundreds of hours of training in aircraft identical to those they would fly in combat. The technical assessment section documented specific capabilities that gave the B-29 decisive advantages. The pressurization system allowed operations at altitudes where Japanese fighters performed poorly and anti-aircraft artillery was ineffective. The defensive armament, integrated with sophisticated fire control computers, created overlapping fields of fire that made close approaches extremely dangerous for attacking fighters. The navigation equipment, including radio direction finders and radar bombing systems, allowed accurate strikes against targets obscured by weather or darkness. The bomb capacity and range combination meant that no target in Japan was beyond reach of B-29 seconds operating from Saipan, Tinian, and Guam. These capabilities resulted not from individual innovations, but from systematic integration of advanced technologies into a coherent weapons system. Fujimoto's report included detailed analysis of B-29 operational doctrine, as revealed through interrogation of the captured crew and examination of flight documents recovered from the aircraft. American bomber doctrine emphasized formation flying for mutual defensive support, precise navigation to targets, concentrated bombing for maximum effect, and safe return to base. Crews were trained to specific tasks: pilot, co-pilot, navigator, bombardier, flight engineer, radio operator, and gunners, with each position requiring specialized skills and extensive training. Japanese bomber doctrine, evolved from different circumstances, emphasized individual aircraft operations, pilot versatility, and acceptance of high loss rates as inevitable. The doctrinal differences reflected different industrial capabilities and strategic priorities. Americans could afford to train specialists and lose expensive aircraft occasionally. Japanese forces required pilots capable of multiple roles and could not sustain significant aircraft losses. The psychological impact of B-29 raids on Japanese military leadership and civilian population received particular attention in Fujimoto's assessment. The sight of American bombers flying at high altitude, beyond reach of defenses, bombing targets with apparent impunity, demonstrated Japanese helplessness in ways that undermined morale and confidence. Each raid reinforced the message that Japan could not defend its homeland against American air power. The captured B-29 examination had shown Japanese technical experts why defenses were inadequate, but this knowledge could not be translated into effective countermeasures without industrial capabilities that no longer existed. The psychological warfare dimension of strategic bombing, not fully appreciated by earlier military theorists, was proving as important as physical destruction of targets. The report's recommendations section presented stark choices. Fujimoto argued that Japan could not win an industrial war against American productive capacity. The B-29 represented just one manifestation of broad American industrial superiority visible in naval construction, ground equipment, logistics infrastructure, and every other aspect of military capability. Attempting to match American production was impossible. Japan's industrial base, even before strategic bombing, was perhaps 1/10 of American capacity. Damage from bombing had reduced Japanese production further, while American industry continued expanding. Any strategy predicated on matching American equipment quantities was doomed to fail. Instead, Fujimoto recommended focusing limited resources on asymmetric approaches that might impose costs disproportionate to Japanese investment. These recommendations included development of specialized high-altitude interceptor aircraft optimized for B-29 combat rather than general-purpose fighters. Such aircraft could sacrifice range, armament, and versatility for climb rate and altitude performance. Concentrated anti-aircraft defenses around critical targets might force B-29 seconds to higher altitudes where bombing accuracy decreased. Nighttime operations and dispersal of facilities could reduce bombing effectiveness. These measures would not prevent American strategic bombing but might make it more costly and less efficient. Fujimoto understood that such recommendations represented desperation rather than viable strategy. The fundamental imbalance in industrial capacity meant that Japan could not sustain any form of conventional warfare indefinitely. The report was forwarded to Imperial General Headquarters in late March 1945. It arrived during a period of catastrophic military reverses. Iwo Jima had fallen after devastating casualties. Okinawa was under invasion, with outcomes clearly unfavorable. B-29 raids were destroying Japanese cities with incendiary attacks that killed tens of thousands and left millions homeless. The technical intelligence report on a captured bomber seemed almost irrelevant amid larger disasters. Yet some officers recognized the report's significance. It documented with precision why Japan was losing and why conventional military responses were inadequate. The insights gained from examining one B-29 applied equally to Sherman tanks, Essex-class aircraft carriers, proximity-fused artillery shells, and every other example of American military technology. American industrial superiority was comprehensive, systematic, and overwhelming. Several copies of Fujimoto's report were retained by officers who understood its historical importance. One copy survived the war in the personal files of a staff officer who surrendered to American occupation forces in August 1945. This copy eventually reached American technical intelligence analysts who were themselves examining Japanese equipment and assessing Japanese capabilities. American analysts found the Japanese report remarkably accurate in its technical details and brutally honest in acknowledging Japanese industrial limitations. The report became a valued document for understanding Japanese perceptions of American capabilities and the psychological impact of technological superiority on enemy forces. The captured B-29 itself met a less fortunate end. As American forces advanced toward the Japanese home islands in spring 1945, orders came to destroy the aircraft rather than risk its recapture. In early April, Japanese technicians stripped useful components and instruments from the bomber, then set demolition charges that reduced the airframe to twisted metal. The destruction eliminated physical evidence of the examination, but the knowledge gained had already been documented and distributed. The technical intelligence derived from one captured aircraft had provided Japanese leadership with accurate assessment of American capabilities, even though this knowledge could not be translated into effective countermeasures. Lieutenant Fujimoto survived the war and the subsequent American occupation. In 1947, he was interviewed by United States strategic bombing survey teams, investigating the effectiveness of strategic bombing campaigns. Fujimoto provided detailed testimony about the B-29 examination and the insights it generated regarding American industrial capabilities. He explained that Japanese technical experts had recognized American superiority by late 1944, but lacked means to communicate this reality to military leadership in ways that might influence strategic decisions. The political environment in wartime Japan did not reward accurate assessments of enemy capabilities when those assessments suggested defeat was inevitable. Fujimoto and his colleagues had documented the truth but could not compel action based on that truth. In 1952, Fujimoto published a technical paper in Japanese aeronautical engineering journals titled Assessment of American B-29 Superfortress Technology, Lessons from Technical Examination of Captured Aircraft. On his wartime reports with classified information removed, documented American advantages in materials science, manufacturing processes, systems integration, and operational doctrine. Fujimoto argued that Japan's defeat was determined not by tactical failures or strategic miscalculations, but by fundamental disparities in industrial capacity. The B-29 exemplified how industrial superiority translated into military capability that tactical skill and operational courage could not overcome. One nation possessed the industrial infrastructure to design, produce, and sustain strategic bombing campaigns. The other nation did not. The paper attracted attention from Japanese engineers working to rebuild their country's aviation industry in the post-war period. Many had served during the war and recognized the challenges Fujimoto described. They understood that creating competitive aviation industry required not just acquiring foreign technology, but developing industrial capabilities for precision manufacturing, advanced materials processing, and systems engineering. Japan's post-war aviation industry, initially focused on repairing American aircraft under contract, gradually developed indigenous capabilities through systematic learning and technology transfer. The process took decades and required partnerships with American companies willing to share knowledge and manufacturing techniques. By the 1960s, Japanese industry had achieved capabilities that were unimaginable in 1945. Companies like Mitsubishi Heavy Industries, Kawasaki Heavy Industries, and Fuji Heavy Industries were producing aircraft components for American manufacturers and developing indigenous designs that incorporated advanced technologies. The transformation from wartime industrial inadequacy to post-war industrial competence reflected lessons learned from examining equipment like the B-29. Japanese engineers understood that competitive aviation industry required investments in manufacturing infrastructure, worker training, quality control systems, and continuous research and development. These investments, made systematically over decades, created capabilities that wartime Japan had lacked. Fujimoto remained active in Japanese aerospace circles through the 1970s and 80s. He gave lectures at universities and technical conferences, sharing wartime experiences and emphasizing lessons about industrial capacity and technological development. He maintained that the B-29 examination had been a pivotal moment in his understanding of modern warfare. Before examining the captured aircraft, he had believed that Japanese technical expertise and engineering creativity could overcome material disadvantages. After examining the B-29, he understood that industrial capacity and manufacturing sophistication determined outcomes in technological warfare. Individual brilliance and tactical innovation mattered, but sustained industrial production decided. Long wars. In 1994, on the 50th anniversary of the B-29's first combat missions, Fujimoto was invited to speak at a symposium in Tokyo, examining the Pacific War from technical perspectives. Now in his 80s, he reflected on the captured B-29 examination and its significance. He noted that modern observers, accustomed to sophisticated technology, might not appreciate how revolutionary the B-29 had been in 1944. The aircraft incorporated technologies that pushed boundaries of contemporary engineering, high-altitude pressurization, remote gun turrets, sophisticated navigation systems, and engines producing power levels that seemed impossible. More significantly, the B-29 represented industrial mobilization that transformed theoretical designs into operational aircraft produced by thousands. Fujimoto concluded his presentation by addressing young Japanese engineers in the audience. He emphasized that technological competition between nations continues in peacetime through commercial aviation, space exploration, and emerging technologies. The lessons from examining the B-29 remained relevant. Industrial capacity matters. Manufacturing excellence determines competitiveness, and systematic investment in research and development creates lasting advantages. Nations that develop superior industrial capabilities can project power, influence events, and shape outcomes. Nations that neglect industrial development become dependent on others for advanced technologies and strategic capabilities. The choice between industrial strength and industrial weakness was ultimately a choice about national destiny. The captured B-29 examination represented a moment when Japanese technical experts confronted unambiguous evidence of their nation's industrial limitations. The aircraft's range, which defied Japanese estimates and rendered homeland defense nearly impossible, resulted from systematic American advantages in engines, structures, materials, and manufacturing. These advantages reflected decades of industrial development, research infrastructure, and educational systems that produced engineers capable of solving complex problems. Japan, in 1944, possessed engineers of equal intelligence and dedication, but they worked within industrial constraints that limited what could be accomplished. Recognition of these constraints came too late to influence strategic outcomes, but the lessons learned shaped post-war development and contributed to Japan's emergence as an industrial power in subsequent decades. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.